Hey, how's it going? Welcome to the first lecture. This is going to cover Monday the 24th. Should make this more evergreen, but whatever. So we're going to talk about alkyne reactions and alkyne halogenation in particular. So alkyne halogenations are very similar to alkene halogenations, right? So let's find some notes here. This first one's pretty rough. Okay, this is epic. We don't have quite almost 10 minutes yet. It'll be fine. So, all right. Hello. Welcome to the first lecture. We're going to talk about some alkene reactions, and we're going to start with alkene halogenation. So, alkene halogenation is similar to alkyne halogenation is similar to alkene halogenation. Right, so remember alkene halogenation, right? You had your alkene, you added Br2 or Cl2, and you made a vicinal dibromide, right? Where your halogens were on opposite sides. When we have alkynes, we have two pi bonds that we can react with. Can you just go away? We have two alkynes we can react with, or two pi bonds. We have one pi bond here and one pi bond here. So the equivalence, the amount of Br2 that we add, or in this case we'll do X2, so X being bromine or chlorine, that we add, the amount we add impacts the number of times to add halogen to our compound. So we can add a halide to each side, or we can add a halide to each side and keep our pi bond. So we can keep a pi bond, or we can add two halides to each side and get rid of our pi bond. Right? And that's going to be determined based on the number of equivalents we use. Right? So if we have one equivalent, Br2, we only have enough Br2 to react with one of our pi bonds, right? So if I have 1 mole alkyne, I have 2 moles of pi bond. So if I say I have one equivalent of Br2, that means I have 1 mole of Br2 for every 1 mole of alkyne, but I have 1 mole of Br2 for every 2 moles of pi bond that I have. So with one equivalent, I will end up with a bromine on each side of my triple bond, but I will keep my pi bond. Right? Your halides. Oh. when you make the vinyl dihalide, so this is a vinyl for double bond, dihalide because you have two halides. When you make your vinyl dihalide, your halides will be trans to one another. They will be on opposite sides of the double bond. Now I add the same alkyne, and I add 2 equivalents of Br2. Now, with this saying, I have 1 mole of alkyne, and now I have 2 moles of Br2, so I have enough Br2 to react with each pi bond of my alkyne. So I will end up reacting with both pi bonds, and I will make my tetrabromide. So this works with chlorine as well. So 1 equivalent Cl2 gets you a vinyl dihalide. Two equivalents Cl2 gets you a tetrahalide. So that slide is really straightforward. So it's like everyone's favorite reaction now. It is the hydroboration. So we can find notes for it. That's right. All right, so hydroboration, we have the same general rules we had for hydroboration of alkenes. You'll notice I will say that a lot. Right, we need to recycle a lot of our same rules. Right, so we have 2 types of alkyne, right? We talked about we have terminal alkynes. Right, so on a terminal alkyne, right, again, our alkyne's at the end of a chain. So we use our standard hydroboration conditions, BH3, H2O2, water, and hydroxide, right? We're going to make an aldehyde. If we have an internal double bond, internal alkyne, and again we do BH3, H2O2, water, and hydroxide, you will end up making a ketone. Right? So same like with hydration, instead of making alcohols, you end up making ketones and aldehydes. Right. The same rule, so hydroboration for an alkene is anti-Markovnikov. You're going to put your oxygen on the least substituted carbon. The same holds true for alkynes. You're going to put your oxygen, like in the terminal alkyne, you're going to put it here on the end. because it has no substituents, it only has a hydrogen, versus the other side which has carbon. So you're going to put that oxygen on the least substituted carbon. That's weird, dude. Thanks, technology. You suck. Alright, go back. Alright, so this is, everyone's favorite mechanism. It's one of my personal favorites. Right, so we'll do a simple one just so it's easy to draw. So we'll do a terminal alkyne. Right, so we'll make an aldehyde. So we're going to have our alkyne, and we're going to have our BH3. We're going to do H, BH2. The electrons from your pi bond are going to come attack the boron. The electrons in the hydrogen boron bond are going to come down and attack this carbon. That's going to give you that structure there. You're going to react with 2 more molecules of alkyne. So you're going to hydroborate until you run out of boron-hydrogen bonds to react with. So we're going to end up making B here and there. So we're going to end up making that compound there, where we have no more boron hydrogen bonds. We only have boron carbon bonds. So each hydrogen that we added, right? We have a hydrogen here on this carbon, here on this carbon, and here on this carbon. So each carbon, each internal carbon gets a hydrogen from the boron, and we put the boron on the terminal carbon. So this is the end of step 1. Right, so we get here at the end of step 1. So then our next step is going to be the oxidation. And again, this is pretty much, the majority of this is the exact same thing that we saw from the alkene reaction, but I figure if I show it to you enough, it'll stick. Right? So you're going to have OHOOH plus hydroxide. That's going to give you peroxyanion plus water, because peroxide is more acidic than water. So we're going to have that add to the boron, fill boron's empty orbital, and then that's going to give us the 8 complex. So we're going to have OOH minus. This is our 8 complex. And now boron doesn't want to be negatively charged, so it needs to give up a bond. And it would prefer to give up a carbon-boron bond than a boron-oxygen bond. Boron really likes oxygen. The boron-carbon bond is a little bit weaker. So we're going to slide these electrons over, and we're going to break our oxygen-oxygen bond, because that is a weak bond. And then that's going to give us B. So we're going to get a little arrow going here. Boom. That's going to give us this structure right here, right, where we've now replaced a boron carbon bond. We've moved it and made a carbon oxygen bond, and we're going to make hydroxide. We're going to do that step 2 more times. Oh, sorry. We're going to do this way. We are going to do this hydroxide, this peroxy step 2 more times. So we're going to repeat the addition. So we're going to do this addition to make an 8 complex, to make this again. And then we're going to shift a different carbon bond, and we're going to keep doing that until we no longer have boron carbon bonds. So we're going to have boron, O, O, O. Right? So now we've replaced all of our boron carbon bonds with boron oxygen bonds. So we've got our carbons. Our carbons now have oxygens on them. Right? So each of our carbons has an oxygen now. Right? And all we have to do now is we've got to get these oxygens off of our boron. Right? So to do that, we've generated, let's draw the right structure, sorry. We've generated a lot of hydroxide, and we have a bunch of hydroxide in the reaction to begin with. So we're going to have these electrons add to the boron and push off an oxygen. Right, so we're going to end up with O, boron, again. Right, we're going to make this, plus we're going to have O minus. So we're going to knock our carbon piece, our carbon-containing piece, we're going to take this off, and it's going to be right here. We're going to repeat that step 2 more times. So we're going to have 2 more hydroxides add. And that's going to give us boric acid. Plus 2 more of these. So we'll just do this with 1 because all the steps are the same. So now we're going to have boric acid, right? As the name implies, it is acidic. We're going to steal a hydrogen from boric acid. Right? Again, this is just like from our hydration mechanism that hopefully we got to in class. This is an enol, right? It is a double bond that has an alcohol on it, an ene with an ol, an enol, right? And enols are not particularly stable, right? They're tautomers, right? And so this has an equilibrium that favors being the carbonyl compound. So once you have the enol, it will tautomerize into the carbonyl compound, either an aldehyde in this case, or a ketone. Oh, I don't know why I did that, it's fine. Right, so just like our hydration, right, if we have an internal alkyne, we're going to want the alkyne to be symmetrical because there's really no way to direct the hydroboration if it's not. So a symmetrical alkyne is going to give us one product, right, no matter which carbon I add to. I add to this carbon, it's here. If I add to, we'll go green, there's so many colors at our disposal. If I add to the green one, right, these are the same molecule, right? If you just rotate the green molecule over, right, you just rotate it around, the two molecules lay on top of each other. So, green molecule, green dot right there. So they end up being the same thing. Right, so when it's symmetrical, you only make one product. If you have an internal alkyne that is asymmetric, right, so let's say something like this. So if I add to blue carbon, I put the boron on the blue carbon and then put the oxygen there, I get that. If I put it on the sweet green carbon, right, I will end up making that. So I'll get two different products. So when you have an asymmetric alkyne, hydroboration will lead to two different products. So our next thing, we have hydrogenation. So hydrogenation is a way to remove pi bonds. So when we had alkenes, we could remove the double bond and get back to alkane. Similar is true for alkynes. Right, so I can go from alkyne all the way, I go from alkyne to alkene to alkane. So depending on what reagent I pick, that says where I will stop along this path. So to get from alkyne straight to alkane, we can use H2 palladium on carbon or platinum. And that's going to remove all of the pi bonds in the molecule. Right. So it really doesn't matter, like if you have double bonds, and then you've got some triple bonds going on. H2, the palladium on carbon, you're just going to get rid of everything, right? So, 3, 4, 5, 6, 7. So you just get rid of all of your pi bonds if you have H2 palladium on carbon. Now we can stop at alkene depending on what reagents we use. So if we want to stop at a cis alkene, right, so we have an alkyne, and we want to get it to alkene, particularly cis alkene. We're going to use Lindlar's catalyst and H2. Lindlar's catalyst is a poison palladium catalyst and is only able to reduce the pi bond of the alkyne. It cannot reduce the pi bond of the alkene. Lindlar's catalyst is palladium on barium sulfate, and then I do believe I'm spelling this right, quinoline. So it's got palladium on barium sulfate and quinoline, and it makes it so you can only reduce the pi bond of an alkyne, never the pi bond of an alkene. So if you have this, and you use Lindlar's catalyst, and H2, we're going to reduce the alkyne. So we're going to reduce here. We're going to make this a double bond, but we're not going to do anything over here. There'll be no reaction over here because Lindlar's catalyst cannot react to double bond. So our product is going to be kind of looks a little goofy, but 1, 2, 3, 4, 5, 6, 7, 8, 9. 3, 4, 5, 6, 7, 8, 9. So we're going to have a cis double bond, and we're not going to react with our alkene at all. Now, Lindlar's catalyst gives us a cis double bond, but if we want a trans double bond, we can get that as well. So you can use sodium and ammonia. So sodium in the zero oxidation state, just straight sodium metal. You just drop a chunk of sodium metal into liquid ammonia. It is super good for you. Super good. Or you can use lithium metal and drop it into liquid ammonia and make the trans double bond. So sodium or lithium in liquid ammonia will reduce your double bond, reduce your triple bond to a trans double bond. Okay. So let's do a simple one here. Just kind of run this one back. All right, so our mechanism . Right, when you have sodium in ammonia or lithium in ammonia, you end up getting electrons off of your lithium or your sodium, and you make a lithium radical. So we're going to have our radical attack our alkyne, and then one electron from our alkyne comes over, and the other electron goes over to the other side. So we're going to have one electron come over, meet the lithium electron, make a bond, and the other radical come over to make a carbon radical. whenever you have a carbon-metal bond, you can think of that bond as being kind of broken in half, right? We can kind of draw a line here and say, hey, the metal side of this bond is positive, and the carbon that that metal is bonded to is negative. So we can redraw this structure as like this, where you have the lithium and the carbon apart, and this is a radical anion. So it is an anion, it is a negatively charged atom, or negatively charged molecule, right here, that has a radical, right here. So we have a radical and an anion. So we have a radical anion. What will happen is the anion part of this molecule, well, first of all, the anion part of this molecule, let me erase this here, will react with ammonia. So we've got all this ammonia around, so it will react with ammonia. And compared to our carbanion, to our negatively charged carbon, our ammonia is acidic. So these electrons will come out and pull a hydrogen off of ammonia. It will give us just a radical. Here's the hydrogen we got, and we make NH2 minus. So right now I have my double bond drawn in the cis conformation, but vinyl radicals are not conformationally stable, meaning that this group right here is free to flip back and forth. So what ends up happening is, as the reaction happens, this methyl group that I have underlined in red will flip up and get away from the methyl group on the other carbon, right? So when these two methyl groups are together, are cis, there's a steric interaction. And those sterics are pushing those two methyl groups apart. So the red underlined methyl group will flip up and away because it's a radical. And now this configuration is so this is more stable than this. So the trans configuration is more stable than the cis. Okay? Once we flip into the trans configuration, what will happen now is that this radical will react with another lithium radical. And what this will give us an anion. Right? So now I have that same carbon metal bond that I had before. Right? I can draw my line plus minus, right? So I should say equal to Right? I'm going to have more ammonia around because I've got a bunch of ammonia. And we're going to pull off that proton. And we're going to make our trans double bond, plus we're going to have more ammonia. And that's how you do that reduction. So these are pretty harsh conditions. So for the most part, you're going to be using, did the weird like wig out thing. So you're going to usually have pretty simple alkynes that you're going to use, but with these conditions, you're just going to go, you're going to take everything that's with your alkyne, and you're just going to go from alkyne to trans alkene. Right? If you have the same molecule and you use Linlar's catalyst, you're going to make a cis double bond. Both of your hydrogens are going to be added from the same side. So we're going to talk briefly in the last few minutes of this video about where alkynes come from. Right. So let's see here. So I guess this is a synthesis of alkenes first. My bad. About where alkenes come from, and then we'll talk about where alkynes come from. All right, so there are two main ways to make alkenes. The first is dehydrohalogenation. Right, so dehydrohalogenation, right, is the exact opposite of hydrohalogenation. So we learned this reaction, right, where you have a double bond, you add like HBr, you're going to put the bromine on one side, hydrogen on the other. This is hydrohalogenation, right? Dehydrohalogenation is doing this reaction in reverse. So we start with an alkyl halide and we remove HBr from the molecule to give an alkene. So we're undoing this reaction, right? So to do this, we have to have a base. Right? So if we have an alkyl halide, and we have a base, we will remove this hydrogen. So our base, which we'll just kind of generically call a B with a lone pair, it can come in, grab the hydrogen, those electrons come down, push out the bromine, and will give you your alkene product plus BH, we'll say plus for right now, keep the charge right, and Br minus. That's plus. There we go. So this lecture is going to be a little shorter just because I couldn't figure out the beginning and I want to make sure I don't get cut off at the end. So hope you enjoy the short one. All right.